Hello and welcome to the Fill in the Blank Programmer. I'm your host, Jason Turner. In this episode, I'm going to be doing a little bit of comparative architecture and compiler comparisons. So this has actually been a hobby of mine since I was in university. I was always fascinated by the differences between different architectures. And there was actually a book that I read, checked out from my university library, probably in 96, 97. I think it was 97. I don't remember the title of it. I tried looking and I'm still not entirely sure. But if anyone knows the title of this book or has an idea what it is, go ahead and post it in the comments. But it was a book that basically covered, well, every architecture that was popular at the time. And it mentioned the different instruction sets and how many registers they had and how the registers were used. And it was like a comparative computer architecture kind of book. I don't know which one it was. But we kind of can do this kind of thing with Compiler Explorer today. So if you don't know me from my other channel, I am host of C++ Weekly as well. And if you're interested, I have C++ puzzle books and C++ on-site training available if you're interested in that kind of thing. But this is not going to be a very C++ heavy episode by any means. This is just going to be a look at different architectures, and you would have already gotten that from the title of the episode. So what we have is RISC-V, RISC-V over here in the left with GCC, and all of these are building with -03. So I've got RISC-V, x86-64, and ARM64. This is also known as ARC64. And that's GCC across the top. Across the bottom, I have Clang. Now this says x86-64, but the actual target down here is RISC-V64. See that here? So I'm doing 64-bit RISC-V or RISC-V for both of them. And if you know the actual way that's supposed to be pronounced, please go ahead and leave a comment. I'm not sure which way they mean for it to be said, and I didn't look that up before starting to record this episode. So then I also have Clang 14 down here, and you'll notice the architecture is not set because this is x86-64. Now we want to do a modern architecture from Intel here just to make sure that we've got like the latest and greatest thing going on. And it's kind of funny, like if I give this an mark and I don't give it an actual flag, if I make up an architecture, let's do that. Compilation failed, and then it'll tell me your target values are whatever. These are all the different possible things. And there are lots of architectures that are supported by our modern compilers. So we kind of have to pick the latest one, and it's actually a little bit of a pain to figure out which one should be supported. So let's go ahead and open up the list of Intel subarchitectures real quick. So we're looking at this list of microarchitectures, and we notice Alder Lake down here. Let's go down to this one. Alder Lake, I believe, is the latest one supported. And let's see, we'll scroll through here. Sandy Bridge, Ivy Bridge, Broadwell, Sky Lake, Canyon Lake, Cannon Lake, Copper Lake, Rocket Lake, Ice Lake, Alder Lake. There we go. So mark equals Alder Lake. Let's just go ahead and do that for good measure on both GCC and Clang so that we are targeting the same architecture on both. And then on the bottom right here, the last one that we have left, this is the ARM64 from Clang again, and I'm doing target equals ARM64 here. Now it is worth noting that every Clang build by default supports all of the architectures that Clang supports. GCC, you have to do different builds that are targeting the thing that you want to target. With Clang, they're all available. So I'm just returning 42 from this function, and we can infer a couple of things. So we can see that in RISC-V, we're getting a 0. You know what, let's just go ahead and look this up. Pronounced RISC-V. Okay, so in RISC-V, we can see that 42 is being returned in A0, and on ARC64, on ARM64, 42 is being returned in W0. So they're both being returned in the 0th register. That makes sense. And x86-64, that's being returned into EAX. It's a 32-bit wide register, and that makes sense because, well, this is a 32-bit integer. On all modern compilers today, int is a signed 32-bit integer. This is not guaranteed. And if we go to something like AVR, it's actually a signed 16-bit register because that's an 8-bit architecture. An integer must be at least 16 bits. So we're getting a 32-bit register return here on x86-64. And this is all pretty straightforward. So we see that A0 and W0 and EAX are used for returning the values, and all three compilers are generating the same code. Both compilers on all three architectures, all 6 combinations, basically the exact same code. So let's go ahead and add x to this value and see how things change. So this is fun. We get 42 added to A0, stored in A0, return. Now that makes sense, I guess. It seems that A0 is both the first parameter to the function and it is the integer return value. So we get 42 added to the input, stored in the output, and return. Let's see if I can make these fonts slightly bigger. And we get exactly the same code on ARM. We get 42 added to W0, returned in W0, return from the function. x86 is the outlier because it has this LEA instruction that's load effective address. And that is something that was intended by Intel for calculating the address of something like an offset into a contiguous array of data stored in memory somewhere. And so it has lots of operations like being able to add constants and being able to multiply by powers of 2. And this was found to be a very fast way of doing these instructions on x86 world. And so people who are handwriting assembly would use the LEA instruction. It goes back to the original 8086. And then compiler writers started using it, and Intel, as far as we can tell, ensured that it was in fact a very, very fast instruction because so many people are relying on it. So that is handy to have this single instruction. So if we do something like add 42 to x times 2, now things start to get pretty interesting. We can see that we've got RDI plus 42. So that is the input register, RDI. It's actually EDI. It's a 32-bit value, but here it doesn't matter because it's the same way of referring to the same value as the same location in the CPU. EDI would be the 32-bit version, RDI is the 64-bit version. So it's going to add the input register plus the input register plus 42 and return from the function. Now, Clang, interestingly, has a missed optimization here for sure, because Clang is doing RDI plus RDI and then a completely separate instruction for adding the 42 into it, and then we return from EAX. So let's go ahead and do a compile to binary. Interestingly, we're getting this internal server error from Clang's compile to binary. I'm not sure why. Here we go. It might seem a little silly to look at this, but let's just go ahead and see that this LEA is 4 bytes, 8D443F2A. And this LEA is 3 bytes, plus another 3 bytes to add the value 42 into the resulting register. So it's a 6-byte program as opposed to a 4-byte. Well, if we add in the return instruction, it's 5 bytes versus 7. And it's multiple instructions. There might be something about parallelization or something here, but I don't think so. I think this is a missed optimization from Clang. So this is where things are starting to get a little bit interesting too with our ARM versus RISC-V comparison. So we add 21 to W0 and store the result in W0. Okay, so now we've got X plus 21. Okay, and then a logical shift left by 1 of W0 and store the result in W0. All right, that's interesting. So that gives us X plus 21, and then it multiplies the entire thing by 2. And GCC made the exact same decision for both RISC-V and ARM. Now, Clang down here, it has said, let's do the shift left by 1 of X, the input register, store that in W8. That's going to be X times 2, which is what we expect. And then it adds 42 to the result of W8, stores that in W0, and returns. That's what it's doing on ARM64. Why it introduced this extra temporary register, I find very interesting. I don't have an answer for that. You can see here that GCC did not. It uses W0 in both cases in its register allocation. And Clang did a little bit for the RISC-V, it did not use a temporary register. We can tell that it definitely didn't need to for ARM64, but it chose to. All right, let's go ahead and keep multiplying this. So multiplication by 4. Now we get RDI times 4 plus 42 in LEA, and we get the same exact optimization from Clang in this case. Now that we did times 4, Clang no longer misses that optimization opportunity. And we get to see that all of these examples have stayed basically the same. It's just now doing a shift by 2 to multiply by 4 instead of a shift by 1. Now notice it did not factor out the 4 in this case. Let's see, 42 divided by 4 is not an even number, so that would be a reason why it didn't. So it'd be curious to see if we do that and it can factor out the 4, if it will. And in fact, we see that GCC does factor out the 4. It adds in the 11 and then it does a multiply by 4. Again, using a shift left. And Clang, in all cases, continues to do the multiply and then the add of the input value. If there's some advantage here, I don't know. But let's multiply by something that can't just be a shift. Okay, so now we're doing times 5 plus 44. And some of these things are fun. In GCC and in Clang, for ARM, we start to see one of the, in my experience, relatively unique things that we can do with ARM instructions. And that is the fact that you can do a shift of any input operand pre anything else happening. So what we see on both Clang and GCC again is that we get a logical shift left of 2 of W0. So that takes W0 and multiplies it by 4. And then we add that to W0. So now we have times 5, and we store the result in W0. And then we add in the constant 44 into W0, restore the result in W0, and we return from function, and there we've got our X times 5 plus 44. It's pretty straightforward. With Clang, we get the exact same code, but again, it's allocating this extra register, which again seems very strange to me that it's going to end up missing other optimization opportunities in the future because it's already allocated that register to something. I would think that minimizing register allocation when you can would make sense, and that's the decision that GCC is taking. But we would have to continue to look at more complicated examples to see that. Now, looking at the x86-64, we get this shift left by 4 that's allowed, plus the addition of the constant 44, plus the addition of RDI again. So that still stays as one single instruction in GCC. And interestingly, all of that is still just a 4-byte instruction. Clang is back to missing that optimization for whatever reason, and it is now just doing the 4 times RDI plus RDI, so that's a times 5, and then adding the constant 44 into it. And then we get over here to RISC-V, and here's where we start to see some of the real differences between RISC-V and ARM. Otherwise, it seems very similar, but clearly RISC-V doesn't have this extra feature that ARM does that lets you do a shift of any operand before working on it. So we've got 2 of a shift left of A0, store the result in A5. So that's our times 4. And then we've got A0, that's the input, again, added to A5. So now we're up to times 5, store that result in A0. And then we add in 44 into A0, store the result in A0, and then we return from the function. So that makes sense. That's the input times 5 plus 44. And we see effectively the exact same thing from Clang, but again, we're seeing a slightly different register allocation. We're seeing A1 used here for a temporary register instead of A5. Why? I have absolutely no idea. If you have an idea why, or if this is just an arbitrary decision, go ahead, please leave a comment. Let's go ahead and add in another value just for the fun of it. Okay, so now we've just added in another value, y. And we're seeing that we have RDI. This is the exact same code. This is 44 plus x times 5 stored in EAX, and then adds in ESI. So that's going to be the Y register. And now we are going to see that A1 on RISC-V is the second parameter to the function, because we see this A0 shifted left twice, that's our times 4, plus A0, that's our times 5, plus 44, plus A1 gets us the plus Y. We see that on both of these. And we see pretty much the exact same code here between GCC and Clang on the ARM side. That at this point we would expect to see. It does the adds in a slightly different order. And yeah, we still see that Clang is allocating W8 to this operation, and GCC is sticking with only the registers that it has to use. Interesting. For a fun experiment, let's take this one back and put it back in a power of 2 and see where we are. Yes, okay. So now it can do the RDI times 8, so because that's a shift left by 3, plus 44 and RSI added into it. GCC manages to keep this as a single instruction, and Clang is back to doing this kind of thing. Exactly what we would expect. And ARM is no surprise, shift left by 3, add in the 44, fine, except for the extra register being allocated. And we see a slightly different order of operations for RISC-V between Clang and GCC, but we've got the shift left by 3. That's interesting. On the RISC-V, GCC is now the one that allocates an extra register when it didn't need to, and Clang sticks everything in A0 and A1, where on Clang with ARM, it does the extra register and GCC doesn't. That's actually quite interesting. All right, let's do something slightly more complicated. We're going to look at a common algorithm for how one might count the number of bits in a value. I need to go look up this exact algorithm to make sure I get it right. I'm going to call this pop count for reasons that will become obvious in a moment. It is literally counting the bits population count. It's counting the number of bits that have been set. This is a common, well-known algorithm that compilers have learned to detect. Yeah, this is a very strange choice here by GCC. See that it's zeroing out EAX at first. That might help with processor throughput because it's telling the CPU ahead of time that it's going to use EAX, which is basically a free instruction to execute to zero out EAX, because the processor, as my understanding is, gives you a new virtual register from its virtual register pool that is EAX, that is defaulted to 0, but then it just calls this single pop count instruction. This could be a missed optimization by GCC, or it could be intentional. There's like register dependency tracking and all these things that happen inside the branch predictor and stuff that I don't fully understand, so I can't really speak about it. But there might be a reason GCC did this, but it looks like a missed optimization to me. So on ARM64, we see that there's this CNT opcode. So this clearly is one that is also doing a population count. And it is counting the number of bits. In S0, it takes W0, stores it in S0, does this operation, and then returns that with an fmove to W0 and returns. And we see, yes, okay, I just verified that CNT does count non-zero bits. And H0 is a 16-bit register, and S0 is a 32-bit register, and the V0 ones are vector registers. And it's interesting to note, okay, we've dissected somewhat this optimization that both GCC and Clang can do. They see that this is a population count. GCC and Clang do the right thing on x86 64 and on ARM, ARC64. On RISC-V, on the other hand, it seems, and I tried looking for this earlier, that there is no pop count opcode on RISC-V, so the compiler has to implement the loop. So we get exactly what we asked for in this case. It's still a fast function. This is one of the faster ways of doing this. Usually this is an exercise to the reader as to how this works, but it does work because clearly the compilers are able to see that here. All right, so that's basic addition, multiplication kinds of things and different ways that the compiler can optimize. Everything else that I can think of is going to be like high-level optimizations. Is it going to do loop unrolling, whatever? That should be the same between these architectures. We could look at some vectorizable code and see what happens there. Okay, it looks like we can't actually use tuple or array in Clang, ARM, or RISC-V. We use tuple? No, not array either. All right, we're going to have to implement these really quick. This comes down to how these compilers are set up and configured on Compiler Explorer. All right, if I did this right, then I should have a bunch of vectorized adds across all of my different platforms. Let's see. I have to admit, I am not very good at reading these things. I see that I'm doing, well, a really, really clean summation on Clang that is doing a loop of 8 adds. And we see that we have a similar loop being formed here on GCC and Clang. I expected, let's take this back. Yeah, it fully unrolls a bunch of vectorized adds for 8 or 16 packed single precision floating point values. And we're getting approximately the same thing on Clang, although Clang looks much cleaner. And then we are seeing, let's see, fadd. That's just a floating point scalar add. So there's no vectorization happening at the moment here on GCC or Clang for ARM. We might be missing something. And then this is fascinating. It's calling a built-in function on Clang with RISC-V to do the adds. and it's not calling that built-in function. It inlined it on GCC to do the floating point adds. This is going to take more homework here. Let's see if we can look at... I see. Okay, I should have been looking at this closer. It is doing vector register additions for these add instructions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, it's doing 16 adds. It's doing 16 4-wide adds, and that's both on Clang and GCC. And we're seeing we're doing clearly more than 16 with RISC-V. Yeah, so it looks like it fully unrolled it. And I don't know what Clang did here. Let's look at that. All right, it looks like it is, well, not yet working to do automatic vectorization of code with either GCC or Clang for floating point operations on RISC-V. I did a bunch of looking around, and it seems that this is, well, difficult to figure out at the moment. It's something that is currently experimental with both GCC and Clang, and trying to get the compiler to do it automatically, I just wasn't able to find the right flags. So that's where we are. With modern 64-bit ARM, 64-bit Intel, we get this kind of thing for free. The compilers automatically support it. They do a pretty good job of it. On RISC-V, it's been a very recent CPU extension, relatively speaking. It just got to 1.0 pretty recently. And, well, we're not going to necessarily see it in our compiler support at just this moment. And this is as of June 1st, 2022, when this episode was recorded. So yeah, I thought this would be just a fun little dive into comparative architectures and comparing compilers against each other for the kinds of assembly they generate. I hope you had fun with it. And again, if you like this kind of content on this channel, be sure to subscribe, leave a comment, let me know what you thought. Thanks for watching.